Hello everyone, welcome to IIT and Gate classes. This is lecture 13 on TOC, and in this lecture we are going to study normal forms. Okay, normal forms are also known as restricted context-free grammars because we apply some restrictions on context-free grammar and we got normal forms. Okay, so let me give you some idea. Normal forms are of two types, CNF and GNF. CNF is Chomsky normal form. GNF is Grayback normal form. In CFG, in context-free grammar, we say LHS implies RHS and LHS exactly one non-terminal and nothing else. Okay, exactly one non-terminal and nothing else in LHS. RHS can be anything. Okay, I hope you remembered my Chomsky hierarchy video. In that video, I have clearly explained you in a context-free grammar, we have LHS implies RHS and LHS is exactly one non-terminal and nothing else. RHS can be anything. Okay, you can keep anything in RHS, but in RHS, when we apply some restrictions, then we get normal forms. Okay, and what are those restrictions? I have shown you here. RHS, in RHS, if we have exactly two non-terminals or exactly one terminal, then we got CNF or Chomsky normal form. And if in RHS we have terminal followed by any number of non-terminals, then we get Grayback normal form. Okay. So LHS is same. That is exactly one non-terminal and nothing else, because after all, normal forms are also context-free grammar. So LHS exactly one non-terminal and nothing else. But in RHS, if we have restriction that exactly two non-terminal or exactly one terminal, then we got Chomsky normal form. And if in RHS we have terminal followed by any number of non-terminals, then we got Grayback normal form. Okay, so let me give you some examples. S implies AB. Is this in CNF? Tell me fast, please. Is this in CNF? Yes, this is in CNF. Why? Because LHS exactly one non-terminal, RHS exactly two non-terminals. Okay, that's why it is in CNF. What about this scenario? Again, similar example, CNF. Again, similar example, CNF. A implies A. Yes, exactly one terminal is allowed. Yes, exactly two non-terminal or exactly one terminal. So small a is terminal symbol, na? Small a is terminal symbol. So I will say that yes, this is also in CNF. What about this scenario? No, this is not in Chomsky normal form. Why? Because right hand side we have null, and null is not a terminal symbol. I have explained you many times. Okay, so null is not terminal symbol. So A implies null is not allowed in CNF. Okay, and few examples of GNF. See here, capital A implies small a. Okay, so this is obviously in GNF. This is in GNF. Why? Because in RHS we have said terminal followed by any number of non-terminals. So if we do not have any non-terminal, then we will have only terminal, and that is allowed. Okay, so see here carefully. Left hand side non-terminal, right hand side single terminal. This is allowed in both CNF and GNF. Okay, now next scenario, next example, terminal followed by any number of non-terminal. This is perfect example. Terminal followed by any number of non-terminals is allowed in GNF, but here we have two terminals. Two terminals are not allowed. We have exactly one terminal followed by any number of non-terminals. So this is not allowed. NA implies null. Similarly, it is not allowed because null is not a terminal symbol. So I can say that null productions are not allowed in CNF as well as in GNF. We have a few important points. So let me jump to next slide to show you some other points about CNF and GNF. Okay, so the first important point is null productions are not allowed in CNF and GNF. I have already told you in this slide that null productions are not allowed. Okay, next is S implies null is allowed. See, null productions are not allowed, but we have one exception, that is S implies null is allowed, but S must not appear in RHS of any production rule. This restriction is similar to your type 1 grammar in your Chomsky hierarchy. Okay, if you remember, then this is the similar restriction that we have studied in type 1 grammar in Chomsky hierarchy. Okay, so S implies null is allowed, S implies null is allowed, but S must not appear in RHS of any production rule. Okay, so null productions are not allowed, but S implies null is allowed. Okay, null production means A implies null, B implies null, C implies null, and so on. Any non-terminal going implies null is null production, but S implies null is allowed. Okay, I hope I have made the point clear. Next is unit productions are not allowed in CNF and GNF. What are unit productions? I hope you already know all these facts, but let me give you some idea. See, if I write here capital A implies capital B, this is an example of unit production. That is non-terminal implies non-terminal. Okay, I have already told you in previous lecture also. That was about your reduction of context-free grammars. I have already told you about what exactly are unit productions, and unit productions are not allowed in CNF as well as in GNF. Okay, why these are not allowed? Simply apply the definition itself. Okay, so RHS exactly to non-terminal. See here, exactly to non-terminal or one terminal. So here we have exactly one non-terminal. So this is not allowed. Okay. Similarly here, terminal followed by any number of non-terminals, but we have got only non-terminal here. Where is the terminal? Okay, we do not have any terminal here. So hence this is not allowed in GNF. Okay. So that's why I have written unit productions are not allowed in CNF as well as GNF. Okay. Next, A implies A, that is non-terminal implies terminal, is allowed in both CNF as well as in GNF because it is satisfied by both the definitions. Okay, so let me show you this in previous slide. I have already told you A implies A is allowed. Okay, so non-terminal implies terminal, like capital B implies small c, and capital D implies small e. These are allowed. That is non-terminal implies terminal. This is allowed in both CNF as well as in GNF. You can check it out from the definition itself. Okay, now let's jump to the next slide. I have given you some questions. Please try to answer them, whether these are in CNF or GNF. See here, exactly to non-terminal, terminal, terminal. So this is in CNF. Okay, this is in CNF. Is it in GNF? No, this is not in GNF. Why it is not in GNF? Because GNF says first you should have a terminal. Where is the terminal here? So this is not in GNF. What about this scenario? Terminal followed by any number of non-terminal. Terminal followed by any number of non-terminal. So this is in GNF. Okay, this is in GNF, but it is not in CNF because CNF says exactly to non-terminal or single terminal. So this is not in CNF. Okay, so these are very simple scenarios. Just apply definition. That's it. Next, S implies yes or null. See, S implies null is allowed, but S must not appear in RHS of any production rule, and S is appeared in RHS of this production rule. So this is not allowed either neither in CNF nor in GNF. Okay, because null productions are not allowed. Okay, and S implies null is an exception, but S must not appear in RHS. But here S is appeared on RHS also. So it is not allowed in CNF as well as in GNF. Okay, this is definition only and nothing more than that. What about this scenario? ASB, BSA, or A? See here, terminal followed by any number of non-terminals. Nah, but here we have non-terminal. Then how we get this terminal? So this is not in GNF. Similarly, this is not in CNF because CNF says exactly to non-terminal. Okay. Now next, see these examples. Okay, so let me write here CNF, GNF. What about this scenario? Terminal followed by any number of non-terminals, terminal followed by any number of non-terminals, terminal, terminal. Okay, so this is in GNF, this is not in CNF. Next, S implies A, B, C, D, E, F, X, Y, C, D, exactly two to non-terminals. Now, see here, exactly two to non-terminals and terminals here. So it is in CNF, but it is not in GNF. Next, A, B, C, D, S, or D. So what about this scenario? See, GNF says terminal followed by any number of non-terminals. But here we have terminals. So this is not in GNF. And this is not in CNF also because CNF says exactly two non-terminal or a terminal. So this is not according to CNF also. Let me jump to next slide. S implies A implies A, B implies B. So this is CNF and GNF. Okay, so this is in CNF also and GNF also. Obviously, because we have here non-terminal and here terminal. Okay, so this is allowed in both. Next, A, B. If you have doubt, please rewind the video and watch it again. I'm not going to repeat it again and again. Please, if you have doubt, please rewind the video. Next, see here, A, B, 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 B. Okay, so what about this scenario? See here, directly say this is a unit production. S implies B is a unit production. Unit productions are not allowed in CNF as well as in GNF. So both are wrong. Next, S implies null. Okay, S implies null is allowed, but S must not appear in RHS of any production rule. S is not appeared in RHS of any production rule. So this is so there is no problem at all. S implies null, no problem. Now terminal followed by non-terminal. Okay, terminal followed by non-terminal, and here terminal only. So this is in GNF. Okay, so you can directly see this is in GNF, but this is not in CNF. Okay, why this is not in CNF? Because obviously we need exactly two non-terminal or exactly one terminal only. Okay, so this is not in CNF, but this is in GNF. Okay, please check it out yourself. This is very simple scenario. Next, S implies AB, A or B. Okay, so obviously CNF and GNF. This is CNF, not in GNF. I'm not going to repeat it again and again. Check it yourself. S implies A or AB, A implies null, C, D, E, F. See, A implies null productions are not allowed in CNF as well as in GNF. So this grammar is neither in CNF nor in GNF. Okay. Now next, see, next is algorithm for conversion. Okay, let me put everything on one slide so that you can easily see it. See, algorithm for conversion of CFG to equivalent CNF. Okay, so now we are going to convert a CFG to equivalent CNF because we are going to show algorithm. That means what, every CFG can be converted to CNF. Yes, we can say that, but we have one restriction, that is any CFG with LG not equal to 5 can be converted to equivalent CNF. Please note it down carefully. LG should not be equal to 5. That means empty language, LG should not be empty. Okay, only then we can convert it into equivalent CNF. Okay, so what about step number 1? Step number 1 is the similar step which I have already told you, that if S implies null is present, then S implies null is allowed now, but if it is present, then then S must not appear in RHS of any production rule. We have already told you. Now they are saying if S implies null is present and S appear in RHS of any production rule, that means what, this is an exception, this is not allowed in CNF. So we will add one augmented production, S dash implies S. Okay, no doubt it is a unit production, but we have rules and regulations to remove unit productions also, so no need to worry about it. So you just remember the step number 1. If S implies null is present, then and S appears on RHS of any production rule, then add augmented production S dash implies S. Step number 2, remove all null productions. Step number 3, remove all unit productions. All. Okay, let me write all here. Otherwise, you will get confused. This is obvious, but we have to write it so that everything should be clearly specified now. So remove all null productions, remove all unit productions, and applies necessary reductions. Okay, what are these necessary reductions? I will show you with examples. Okay, so let me jump to questions. You will get the idea. S implies A, B, C, D, X, Y, Z. This is your grammar. Okay, please do not say that where capital X is going, where capital Y is going, where capital Z is going, we have not specified, and so on. So I have written, you can say I have written a part of grammar. Okay, and or you can say one production rule of grammar, and I want to convert it into CNF. Okay, so let me show you here how to convert it into CNF. Okay, so the idea is very simple. CNF says RHS exactly 2 non-terminals and or either 1 terminal. This is the basic idea of your CNF. Okay, CNF idea is this, and I have already told you the algorithm how to convert CFG to CNF. So step C, I will apply step by step. Step number 1 will be bypassed. Why it will be bypassed? Because S implies null is not present. Okay, step number 2, remove all null productions. There is no null production, so it is also bypassed. Step number 3, remove all unit production. This is also bypassed because no unit production. Step number 4 is apply necessary reduction. So now I'm going to apply some reductions here. So see here properly. See, idea is RHS exactly 2 non-terminal or 1 terminal. So let me do it for you. So first of all, I will convert it into, say, these all are terminal symbols now. So we do not need terminal, we need non-terminal only. So I will write like this: capital A, capital B, capital C, capital D, X, Y, Z. Capital A goes to small a, capital B goes to small b, capital C goes to small c, and capital D goes to small d. Of course, this grammar is equivalent to this one. Okay, so this is obvious thing, you can easily see here. So see carefully, these all are in CNF, no problem at all. What about this scenario? Okay, so there are multiple ways of conversion. So let me show you one way. One way is you write like this: S implies A1. Okay, so A1 will produce all these things. So I will write here A1 implies B1. Now B1 will produce all these. So B1 will say, B1 will go to capital C, C1. Okay, now C1 will give all these D, X, Y, Z. So C1 will give D1. Okay, I hope now you have got the idea. Okay, D1. Now D1 will give you X, Y, Z. So D1 will give you X, and in place of YZ you can write X1, and X1 will give you YZ. That's it. Okay, so this is the conversion. And similarly, I have to write all these also. A implies A. Okay, so let me write here, or let me copy paste here itself. So these all will be copy pasted here. So I will say that this is the converted grammar. This is the converted grammar for this. Okay, so S implies A, B, C, D, X, Y, Z. This is your given grammar, and the equivalent CNF will be this. Okay, I hope I have made the point clear to all of you. So Okay, so the basic idea here is if we have more than two non-terminals, if we have ABC, say if we have like this, S implies ABC. So I will say S implies A1, and this A1 will produce BC. That's it. So we got exactly two non-terminals in RHS of every production rule. Okay, so if we have three, then you will convert it into two production rule like this and so on. Okay, I hope I have made the point clear. Next question, S implies A, B, C, D, E, B implies B, D implies A. So how will you convert it into CNF? Again, very, very simple task. The basic idea is, see here, step number 1, bypassed because S implies null is absent. Step number 2, unit productions are absent. Sorry, null productions are absent. First we have to remove null production. Okay, please note it down also. Step number 1, 2, 3, 4, you have to apply them in sequence. Please do not disturb the sequence, otherwise everything will be disturbed. Okay, so first you have to remove null production, then you have to remove unit production. Okay, so step number 2, null productions bypassed. Step number 3, unit productions bypassed. Now step number 4, apply necessary deduction. So now I'm applying. So the basic idea here is again same. This is terminal na. So in CNF we do not need terminal. We need only non-terminal. So just convert it into non-terminal. A, B, capital C, capital D, capital E. Okay, so capital A goes to small a. Okay, capital C goes to small c, and capital E goes to small e. Now capital B goes to small b, capital D goes to small a. Okay, so I have copy pasted these two, and this I have got it from here. Okay, so I hope I have made the point clear. Now these all are already converted in CNF. What about my this scenario? Okay, this is again very, very simple. I have already told you the basic idea. So let me show you again. S implies, I will say S implies A1 implies B, B1 implies C, capital C, C1, and C1 implies DE. And copy paste all these. So let me do it for you. Capital A implies small a, capital C implies small c, capital E implies small e, capital B implies small b, capital D implies small a. That's it. So this is the converted. Okay, so this is the converted what CNF for the given grammar. Okay, so let me do put everything on one slide so that you can easily note it down. Okay, note it down carefully. So for this grammar, this is the equivalent CNF. Why I'm calling it as equivalent? Because if this is G and this is G dash, so LG will be equal to LG dash. That means language generated will be same. That's why I'm calling them as equivalent. So I'm saying that G is equivalent to G dash. Okay, now let's move to next question. S implies AS and null. Step number 1. See here, S implies null is present and S is appearing on RHS also. So you have to apply augmented production. S dash implies S. Step number 2. Remove all null productions. Okay, so after step number 1, we should write grammar properly. Otherwise, you will get confused. So after step number 1, S dash implies S. S implies AS or null. Augmented means what? Extra. Okay, so let me write here also. So add augmented production as this implies as now. Augmented means extra production. Okay, the augmented, I think you should know. This is an English word. If you do not know, then I have given you the meaning of augmented. That means extra. Okay, so now let's move to the slide. Okay, so S dash. So after step number 1, okay, this is step number 1. After step number 1, we got S dash implies S implies AS or null. Okay, what about my step number 2? Let me write here. Step number 2 is what? Remove all null production. So do we have null productions? Yes. S implies null is present. So what we are going to do is, please note it down carefully. Now because we have added an augmented production, so our new start symbol will be S dash and not S. Okay, so new start symbol is S dash. This is the basic meaning of augmented production. New start symbol is S dash. Okay, so S is now no longer start symbol. S dash will be our start symbol. So S will be treated just like your only a non-terminal, and this non-terminal is giving us null. So this is a null production, so you have to remove it. Okay, so let me do it properly. S dash implies S, S implies AS or null, so I am removing it. So if you do not have idea about how null productions are removed, please watch my previous lecture. I am not going to explain it again and again. But just for a summary, I am repeating that as see, if you want to remove s implies null, then write the grammar as it is. Of course, s implies null won't be added. Now in right hand side, if you find any s, then hide it and write the remaining part. So here s will be hidden, remaining part is a. Here s will be hidden, remaining part is null. Okay, so this is your final grammar after removing null productions. And see here, now since our new start symbol is s dash and s dash is going to null and s dash is not appearing in RHS of any production rule, so our definition is fulfilled of CNF. Okay, so till now no problem at all. Please note it down carefully. S dash implies null, we have null production, s dash implies null, and s dash is our new start symbol and it is not appearing in RHS of any production rule. So what? So I will directly say that no problem according to definition of CNF. Okay, now next step number 3, remove all unit productions. Unit production remove. See, we have only one unit production, that is s dash implies s, so remove it directly. Okay, so I will say in place of s. If you do not know how unit productions are removed, please watch my previous lecture. Okay, but I will say you in precise, or you can say very shortcut manner. In place of s, apply all the RHS. Okay, apply all the RHS of s here. So it will be s dash implies as or a or null. Okay, now s implies as or a. That's it. Now you just apply necessary reduction. Step number 4. Reductions are what? See, we want what exactly we want? We want exactly two non-terminal or a single terminal. So two non-terminals. Now, so let me write here as s implies as a or null. S implies capital AS or A. Okay, and this capital A will goes to small a. That's it. So we have done the reductions also. Okay, so see here carefully. This capital, this small a, I am replacing it with capital A. Now, this small a, I am replacing it with capital A, and this capital A will go to small a. That's it. Okay, so we have done our remaining things. That's it. So I hope I have made the point clear to all of you. And some of you might get the doubt that, sir, s implies a was already present, so why we are writing capital A? We can replace it by capital S also. No, we cannot replace, because it will disturb our language. Please, this is homework for you. Please try to get your answer. Okay, so that why we are not replacing this small a with capital S. Okay, because if we replace it by capital S, then obviously this capital S will be replaced by a, and this capital S can be replaced by AS also. So that may create some problem. Okay, so make proper habit that if we have got a terminal here, so add a new non-terminal. Okay, replace it with a new non-terminal. That's it. Okay. So I hope I have made the made point clear to all of you. So please note it down carefully, and I'm jumping to next slide. Okay. Yeah. So the next slide is next question. That is s implies ASA, AB, A implies BS, B implies B or null. So step number 1, see s implies null is present. See here, s implies null is present. No, s implies null is not present. So we are not going to add augmented production. What about my step number 2? Step number 2 is you have to remove all the null productions. So see here carefully. Do we have null productions? Yes, we have null productions. So remove it carefully. So I am going to remove now. See, I will write s implies ASA, AB, A implies B, or S, B implies B. That is, you have to write entire grammar as it is, except B implies null, because I am removing B implies null now. Because I am removing B implies null. Okay, so I will write grammar as it is. Okay, and of course I will not write B implies null, and I will hide the B and write the remaining part. Okay. So I will hide the B here. See, we have B in the right hand side now. So hide the B and write the remaining part. That will be small a. Here also hide the B and write the remaining part. That is null. Okay, that's it. Now we have got a new null production, that is A implies null. So try to remove it. A implies null. If you remember this question, I have already solved it in the previous lecture itself. But I am just revising it. Okay, I am moving on in a faster pace, because I think you have already watched that lecture. and you already know the basic things. Okay, so I will write S implies A as A B or A implies B as B implies B. Now we are going to remove A implies null. So here we have got A. So hide the A and write the remaining part, that is AS. Then hide this A and write the remaining part, that is SA. Now hide both the A's. If we hide both the A's, we get S implies S, and it is meaningless. S implies S, this is obvious also. So I'm not going to write it S implies S. Okay, that's it. So we have got here. Okay, so yeah, we have removed A implies null also. Okay, now try to remove null unit productions. Okay, so now I'm jumping to step 3, that is unit production removal. See here, do we have unit productions? Yeah, we have unit productions. Okay, so let me delete all those unit productions. So finally I will write S implies ASA, AB, A, AS, SA, A implies, see, capital B na, so capital B will be replaced by small b, and capital S, this is also unit production. So I'm going to write everything here. In place of capital S, I'm going to write everything here. A, S, A, B, A, S, or S, A. And B implies B. That's it. So we have got, we have removed unit productions also. Now the next step will be what? Next step will be apply necessary reductions. Okay. So step number 4. Step number 4 will be apply necessary reductions. So how we are going to apply reductions? Again, very simple. See here, S implies ASA na. So you will write AX and X goes to SA. Directly write so that you do not get confused. So here we have small a, capital B na. So write here. See, now you cannot say capital A goes to small a na. So let me take a new non-terminal. Let us take as D. So DB, and D is going to small a, right? Side by side so that you do not get confused. Small a, obviously this is in CNF. Capital AS, yes, this is in CNF. Capital SA, this is in CNF. No problem at all. Now next is A implies small b. A implies small b is in CNF, no problem. ASA, so I have already told you, take it as AX. Okay, next is DB. Okay, copy paste all these things. Then we have A, then we have AS, then we have SA. That's it. Okay, so this is my final grammar. Okay, this is the final CNF for the given CFG. Okay, so let me put everything on one slide so that you can note it down carefully. Okay, I think it's not visible, or we have got everything on one slide. So please note it down carefully. Okay, please note it down carefully. Okay, so this is the way to convert a given CFG to CNF. Okay, now next, advantages of CNF. See, we have 4 basic advantages of CNF. Let me read it out for you. The first point is number of steps needed. Okay, number of steps needed to generate string of length n is 2 n minus 1. That is, we have fixed number of steps. Please note it down carefully. We have fixed number of steps to generate any string. Okay, so to generate any string of length n, we need 2n minus 1 steps. How we will prove it? See, this is very simple scenario. Let me give you basic idea. Of course, I will not go into more details, but I am giving you just basic idea. S implies AB, A implies CD, okay, B implies EF. Okay, so if you want to generate any string, then you will apply S implies AB. Okay, now this A will be replaced by CD and this B will be replaced by EF. Okay, or let me do it step by step so that you get the proper idea. S implies AB. This is our first step. Second step will be this A will be replaced by CD. Second step will be this A will be replaced by CD. Now this B is copy pasted as it is. Now third step will be what? Third step will be this B will be replaced by EF. Third step will be this B will be replaced by EF. So you have got in 3 steps CDEF. Okay, now let me write some more you can say productions. C implies D, D implies E, E implies F, and F implies G. Okay, now you see here carefully, you have got 4 known terminals. Now in step number 4, you will replace this capital C by small d. Okay, so small d, capital D, E, F. In step number 5, you are going to replace capital D by E. Okay, in step number 6, you are going to replace capital E by F, and in step number 7, you are going to replace capital F by G. So to generate string of length here, see carefully, to generate string of length 4, what exactly you have done? First step is you got 4 length non-terminal. Okay, so sentential form of length 4, and all these 4 symbols are non-terminal itself. Okay, so step number 1 is to get string of length 4. To get string of length 4, step number 1, get sentential form of length 4 with all non-terminals, with all 4 symbols as non-terminals. This is step number 1. Okay, so what do you think? How many steps or how many production rules are needed to get 4 symbols non-terminal? Okay, or a sentential form of length 4. Okay, so we need obviously 3 steps. Why? Because first step has given us 2 non-terminals. Then in second step, 1 non-terminal is added. In third step, 1 more non-terminal is added. That means each and every step is giving us 1 non-terminal, except the first step, which is giving us 2 non-terminal. So obviously we need n minus 1 steps. Okay, so for this we need 3 steps. Okay, we need 3 steps. Now we are jumping to step number 2. In step number 2, replace each non-terminal by a terminal. So obviously, how many steps we need? 4 steps. So 3 steps generalize, I can write it as n minus 1 steps. 4 steps generalize, I can write it as n. So overall we need n plus n minus 1, that is 2n minus 1 steps. Okay, so this is very, very simple scenario. Just try to note it down carefully. If you have any difficulty, then please rewind the video and watch it again. Okay, so let me put everything on one screen so that you can note it down easily. So please note it down carefully and try to analyze what exactly I have done here. Okay, yeah. Now, so a number of steps I have already explained. So this is a big advantage of CNF now, because number of steps are fixed. So apply 2n minus 1 steps. If you got the string, then it's okay. Otherwise, the string is not, you can say, generated by the given grammar. You can say it. Okay. So if we have a string, or let me put it properly, if we have a string of length n, okay, then apply 2n minus 1 steps. Okay, all possible strings generate using 2n minus 1 steps. If n is if we got string w, then it's okay. Otherwise, you will say no, the string does not belong to the language generated by the grammar. So this is a big advantage. Okay, so if we have a string of length n, and we want to know that this string will be generated by the grammar or not, we have a string of length n and we want to know this string will be generated by the grammar or not. So just apply 2n minus 1 steps, and all possible strings, try to generate all possible strings using 2n minus 1 steps. And if w is generated, then it's okay. Otherwise, you will say that this string does not belong to the language generated by the grammar. Okay, I have repeated many times. If you are able to follow, then it's okay. Otherwise, rewind the video and watch it again. Okay, next advantage is it can be easily stored in computer because length of each production rule is fixed. This is very, very big advantage. See here carefully. Either see the production rules are of either length 3 or length 2. I am talking about total length, LHS plus RHS, length 3 or length 2. Okay, so these can be easily stored in computer, and CFG cannot be stored because cannot be stored easily because in RHS we can have anything. So one production rule can have 100 symbols, another production rule can have only 3 symbols, and so on. So that will create problem for us. So this CNF can be easily stored in computer. This is big advantage. Okay, and if you want to go into implementation detail, then I can say define 2D array. See here, 1, 2, 3, 4, 5, 6, 7. So define a 2D array in C. I am talking because C language is in the syllabus of many competitive exams. So 1, 2, 3, 4, 5, 6, 7. So 7 rows and how many columns? A maximum 3 columns, na? So write it here 3. That's it. Okay. So define this array, and in this array you can store this grammar very easily. Okay. I hope I have made the point clear to all of you. Okay. Next is parse tree will be a binary tree. This is also obvious thing. If you see here carefully, if you want to make a parse tree, okay, for the string DEFG, for the string DEFG, that parse tree will be obviously a binary tree. Why? Because RHS exactly to non-terminal or a single terminal. So obviously it will be a binary tree, and it can be easily stored in computer also. Next, CYK algorithm. Actually, CYK is a membership algorithm. Okay, CYK is the membership algorithm for CFG. CYK membership algorithm for CFG, context free grammar, can be applied only if CFG is in CNF. Okay, so we are not going into detail of CYK algorithm because it is out of scope of this course, because this is a fundamental course. So I'm giving you just idea that we give a CYK algorithm is a membership algorithm. Membership algorithm means, okay, membership algorithm means you will give context free grammar. Okay, you will give context free grammar and a string W. You can give any context free grammar, write it properly, any context free grammar and a string W, and you give that to CYK algorithm. You give it to CYK algorithm, and it will give you answer as yes or no. Yes means what? This W belong to language generated by grammar G. No means this W does not belong to language generated by grammar G. Okay, so CYK algorithm, I am telling you time complexity also. Also, even though it is not needed for you, but I am showing you. Okay, so in advanced course, I will give you proof and all those things, but I'm just giving you idea. Okay, so it will be order NQ, where N is the length of string. Where N is the length of string. Length of string. Okay, so order NQ is the complexity of CYK algorithm. Okay, so CYK membership algorithm for CFG can be applied only if CFG is in CNF. Okay, I hope I have made the point clear to all of you. If you have any doubt, then please rewind the video and watch it again. And let me put everything on one slide. Rather, it's I think it's impossible to put everything on one slide. So please note it down carefully. Please note down all these 4 points and this thing carefully, and this also you note it down. Okay, that's it. So this is all about advantages of CNF. Now we are jumping to next, that is algorithm to convert CFG to equivalent GNF. Okay, so any CFG can be converted to equivalent GNF also. So, but the restriction is that LG should not be equal to 5. Okay, because we are showing you algorithm to convert CFG to GNF. So I can say that any CFG can be converted to GNF, but no, it is not the case. See here carefully, I have written very nicely that any CFG with LG not equal to 5 can be converted to equivalent GNF. Okay, so see here steps. Step number 1 is S implies null. If S implies null is present and S appear in RHS of any production rule, then add augmented production S dash implies S. This is these 3 rules are copy pasted from the CNF examples. Okay, so CNF example, these 3 rules are copy pasted. That is remove null production, remove unit production. Now step number 4 was apply necessary deduction, but here step number 4 is remove left recursion. I will show you by example what exactly is left recursion. Okay, so just wait for 2-3 minutes. Even next slide will be about left recursion only. So step number 4 is remove left recursion, and step number 5 is apply necessary reductions. Okay, so let me put everything on one slide, and then please note it down. Okay, then you can note it down. So please note it down here. Now I'm jumping to the questions. Okay, and firstly I will show you about left recursion, and then I will show you some examples for conversion also. So let me jump to next slide. Left recursion removal. See, first of all, you should know what exactly is left recursion. See here, S and S. This is left recursion. Okay. So what about this scenario? S implies AS or B. This is right recursion. See, S and S. So this S is in extreme right, na? That's why it is right recursion. And here this S is in extreme left, so that's why it is known as left recursion. S and S are matching. Okay, so recursion means, I think you know everything. Okay, I do not need to explain everything here. So this is right recursion and this is left recursion. Okay, so let me say it here like this also, or you can say like this also. So this is left recursion, this is right recursion. So S implies A. Is this left recursion? No, this is not recursion at all. These are not same na. S, so here we should have S only. Okay, so I hope you have got the idea about what exactly is left recursion. So we want to remove it now. Okay, this is your step number 4 now, remove left recursion. So let me show you how will you remove left recursion. Okay, so first of all, tell me something about the language generated by this grammar. Okay, now concentrate here properly, leave all these things, or let me remove all these things so that you do not get any distraction. See here carefully, this is your grammar. So I want to ask you about LG, language generated by grammar will be what? So let me show you a past tree. You will get the idea. S implies SA, S implies SA, S implies SA. You can apply this production any number of times, and then S will be replaced by B. So you will get the string B triple A. So let me give you idea about LG. LG will be smallest string will be B. Then you will have BA, then you will have B double A, then you will have B triple A, dot, 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 dot. Okay. So if I write it carefully, you will get the LG as BA star. Please see it carefully. BA star is the language. So this is your language. Now, if we want to remove left recursion, then obviously language generated by that grammar should be obviously same as this grammar. So how will you remove left recursion? See here carefully. See, you want what? After B, you need any number of A's, na? So you should write B, Z. Now, this is the responsibility of Z to generate any number of A's. So you can easily generate any number of A's by Z, like Z implies AZ or A. Okay. So, and here, okay, you should also say S implies, let me show you carefully. See, if I write this, if I write grammar like this, okay, if I write grammar like this, then can I say language generated by these two grammar will be same? See carefully. Can I say language generated by this and this grammar is exactly same? Language generated is same or not? See here carefully. No, language generated is not same. Why it is not same? See the boundary conditions. Smallest possible string generated here is a single B. Now, can you get a single B from here? No, we cannot get single B. Why? Because you have to apply S implies BZ. Now this Z will be replaced by A. So you will get smallest string as BA. You won't be able to get single B. So that's why you have to write single B here. Okay. So now these two grammars are equivalent. Okay. So I hope you have got the idea that how I have designed this. So I will say, see, let me write it again so that you get the idea. S implies SA or B. This is your left recursive grammar. Now I want to convert it into right recursive grammar, or you can say I want to remove left recursion from it. So after removal, the basic condition is language generated by both the grammar should be same. Otherwise, we will say that it is not a conversion. So how will you guarantee that language generated will be same? So I will say, see here carefully, I will say S implies B na. So directly say B. Then you will say B, then B followed by any number of A's. So you will say BZ, and this Z goes to AZ or A. Okay, I hope I have made the point clear to all of you. So please note it down carefully. And this is the first example. If you have not got the idea properly, then no problem. I am going to solve many examples. You will get the idea. Please note it down carefully. Next slide. S implies SA, B or C. So see the language generated by this grammar. I hope you have got the point. Language generated will be B plus C A star. I have written it in a faster manner. Please try to analyze yourself. This is homework for you, and you have to imagine that why I have written it like this. So obviously, now when I am going to remove the left recursion, I will say B or C. Na? So write this as it is, B or C. Then you will say after B, we can get any number of A's, or after C, we can get any number of A's. Now, any number of A generation will be done by Z. So Z will give us AZ or A. That's it. So this is our converted grammar. Please note it down carefully. I'm jumping to next slide. If you have still not got the idea, then I'm showing you next example also. S implies SA, SB, C or D. So try to get the language. I am showing you the language C plus D, and here A plus B whole star. How I have got it? See here carefully. S implies C or S implies D. Now C followed by any number of A's or B's. Please see here carefully. After D, we can get any number of A's or B's. If you have any difficulty, then see, I am showing you. S implies SA or SB or SA or SB. This S will be replaced by C or D. So let me replace it by D. So what is this? Any possible string over A and B, and this is D. So D followed by any possible string over A and B. Any possible string over A and B is written like this: A plus B whole star. So C plus D, A plus B whole star. I hope I have made the point clear to all of you. Now try to remove left recursion from here. So I will say S implies C here. CD na. So write C D as it is. Now you will say C Z or D Z. Now responsibility of Z will be to generate this any possible strings over A and B. So Z will say that AZ or BZ or A or B. That's it. Okay. And with guarantee, I am saying you that these two grammars will be equivalent. This is homework for you. Try to generate strings and get the answer yourself. Similarly, here also, this and this grammar will be equivalent. Try to take strings and try to match yourself. Okay. Similarly, here also, this and this will be exactly equivalent. Okay. Take some strings and get your answer. Okay, now I'm slowly building the generalized concept or identity. So, but before that, let me show you this thing. So remove left recursion. I will directly say A implies beta 1 or beta 2 or beta 3. Okay, write them as it is. Then then we will apply beta 1z. Okay, beta 1z, then beta 2z, then beta 3z. Now Z will give us alpha 1z, alpha 2z, alpha 3. Alpha 3 is not present. So alpha 1z, alpha 2z. Then we will get alpha 1 or alpha 2. That's it. So this is the basic conversion. And with guarantee, I am saying you that these two are equivalent. Okay. Now we have now we are enough mature, and we will show you generalized concept. So A implies A alpha 1, A alpha 2, alpha 3, dot dot dot, A alpha n, beta 1, beta 2, beta 3, dot 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 up to beta m. So how will you remove left recursion? I will say write them as it is. Step number 1, write as it is. Beta 1 or beta 2 or beta 3, dot 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 beta m. Now you will fix Z after them. That means you will say beta 1z, beta 2z, beta 3z, dot 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 beta m z. Now Z will give us all these things: alpha 1, alpha 2, and so on. So alpha 1z, alpha 2z, alpha 3z, dot 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 alpha and z, and write them as it is also without z. Alpha 1, alpha 2, alpha 3, alpha 4, dot 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 alpha and that's it. Okay, so this is the generalized identity, and this has come in GATE as well as NET. Okay, so many competitive exams have given lots of questions on this identity, and this identity as it is has been asked in GATE as well as NET. Okay, please note it down carefully. Now let's jump to the next slide. So now I will show you necessary reductions. Okay, so see here. Okay, so first 3 steps are copy pasted from your CNF. 4th and 5th step are different. I have explained you 4th step. Now I am going to show you 5th step. Okay, of course necessary reductions will not be similar as CNF. These will be different. So let me give you some idea about necessary reductions. So I have given you the first question itself. So leave everything and try to apply the algorithm. Step number 1, S implies null is present and S is in RHS, so it is not the case. Step number 1 is bypassed. Step number 2, null productions, no null productions, so step number 2 bypass. Step number 3, unit productions, no unit productions, so it is also bypass. Step number 4 is your left recursion, there is no left recursion, so bypass. Step number 5 is left, that is reduction, so I am going to apply reductions here. So very simple. See, this is very simple. We are saying what in GNF, terminal. See, LHS implies RHS. Let me revise you one more time. LHS implies RHS. LHS exactly one non-terminal. RHS terminal followed by any number of non-terminal. This was the case, na? Terminal followed by any number of non-terminal. So we have here a terminal. If we have terminal, then no problem at all. It is very easy task to convert the given CFG to GNF. Okay, so why I'm saying it is very easy. See here. Okay, so I will say S implies A. These are non-terminal, na? We want terminal. Sorry, these are terminals and we want non-terminals. So very easy. I will write it as capital B, capital C, capital D, X, Y, Z, W. Capital B implies small b, capital C implies small c, capital D implies small d. That's it. So this is your converted GNF. These two are equivalent. Okay, and please do not say that, sir, you have not given a complete grammar. Yeah, of course I have not given you complete grammar. I have not told you about where X is going, where Y, where Z, and where W are going. So this is a part of grammar, and I have shown you how to convert this a single production rule into your GNF. Okay, I hope I have made the point clear to all of you. So remember this fact that if you have first terminal, then no problem at all. We can convert the given production rule into GNF very easily, and this is the best example. Next, let's move to next question. S implies capital A, 2 times capital A, then A goes to small a capital A, small b capital B, small c capital D, small e. So how will you convert it into GNF? See here carefully. Here we do not have terminal here. If we do not have terminal, then obviously it will be difficult for us to conversion into GNF. Okay, this CFG can be converted into GNF. You can say it's not easy, or you can say it's not direct. Okay, but let me apply algorithm. Step number 1, S implies null, S is in RHS. It is not the case. Step number 1, bypass. Step number 2, null productions are not present, bypass. Step number 3, unit productions are not there, bypass. Step number 4, null, you can say left recursion. We do not have any left recursion, so it is also bypassed. Step number 5, that is apply necessary reduction. So we have to apply it. Now I'm showing you reduction. This is very actually see, if we have a terminal here, then there is no problem at all. But here we don't have terminal, we have non-terminal. So in that scenario, just replace that non-terminal. Okay, so I will replace that non-terminal with all these you can say production rules, because A is going here now, so replace them. But before replacing, see carefully, each and every production rule is in GNF. See here, terminal followed by any number of non-terminal, terminal followed by any number of non-terminal, terminal followed by any number of non-terminal, and a single terminal. So all these are in GNF. So I will not face any kind of problem, and I will say you directly S implies A, copy paste this A here, B, copy paste this A, C, D, copy paste A, E, capital A. Okay, so I have copy pasted just this capital A after this. Now this capital A will go to small a capital A, small b capital B, small c capital D, and E. That's it. So this is your converted GNF. Okay, and these two are equivalent. This is homework for you. Just try to match it yourself, and this is obvious also. Please note it down carefully. Jumping to next question. S implies SA and null. Again, this is a good question. Step number 1. S implies null is present. S is in RHS. Apply augmented production. S dash implies S, and S implies SA or null. This is step number 1. Step number 2. Remove null productions. Yeah, we have S implies null as a unit production. Sorry, S implies null as a null production. I will remove it. And again, I'm repeating, I have already told you this in your CNF also, that now your new start symbol is S dash. S is no longer your start symbol. Okay, so S implies A, you have to remove. So I will write the grammar as it is. S implies S. Okay, S implies S. S implies SA. I will write the grammar as it is. because I am removing s implies null, so of course I will not write s implies null. And in right hand side, I will hide the s and write the remaining part. Hide this s, write the remaining part small a. Hide this s and write the remaining part null. Now we got s dash implies null, and it won't be problem for us because s dash is your start symbol, and this start symbol s dash is not appearing in RHS of any production rule, so it won't create any problem for us. Okay, so step number 2 is completed. What about my step number 3? Remove null unit productions. So where is the unit production? S dash implies s, so remove it. So in place of s, I will copy paste it. SAA null, s implies SAA. Okay, so in place of s, I will write all these two production rule. I have written that. Okay, so we have got this after step number 3. What about my step number 4? Left recursion you have to remove. See here carefully. Do we have left recursion? Yes. S implies S. This is a left recursion. So very, very easy. I will directly remove it. I will say S implies. So first write like this. S dash implies SAA or null. Now I am removing this left recursion SS. So I will write this first. This is beta 1. Na? Okay, so let me label it for you so that you get the proper idea. Let me use a different color. A implies A alpha 1 beta 1. So you will write beta 1, then beta 1 Z. Okay, beta 1, then beta 1 Z. Z goes to alpha 1. Alpha 1 is A na, alpha 1 and alpha 1 Z. That's it. So we have removed your left recursion from this grammar. Step number 4 is completed. Now you have to write step number 5. So let me write here. That is apply necessary deductions. See, S dash implies A. This is already converted. S dash implies null is already converted. S implies A already converted. AZ already converted. Z implies A already converted. AZ already converted because terminal followed by any number of non-terminals. See, apply the definition of GNF, you will get the idea. Okay, this is not converted now because terminal followed by any number of non-terminal, and here we have got non-terminal. So I have already converted capital S into GNF. So I will copy paste this here. Okay, so I will write it as S dash implies. See, I will write this capital S. I will put the, you can say, I will replace this capital S with the RHS. So I will write here A. Then this A will be copy pasted. Na? This A will be copy pasted. Please write it yourself. I'm not going to explain it again and again. AZA, A null. Then S implies A, AZ. Z implies A, AZ. Now see here carefully. Again, this is giving you problem, but this problem can be solved easily because at least we have got first as terminal. First symbol is terminal, so no problem at all. I can do it in a very faster manner. So I will directly say S dash implies A capital A, then A Z capital A, then small a, then null. S implies small a, AZ. Z goes to small a, AZ. Capital A goes to small a. That's it. So this is your converted grammar. Please note it down carefully. Okay. If you have any doubt, please rewind the video and watch it again. I'm not going to repeat it again and again. Let me put everything on one slide so that you can note it down carefully. Okay. Now next. S implies double A, A implies double S or B. Okay, this is your grammar. Okay, so this is your last question. Okay, so how will you do it? Again, very, very simple. Just apply the steps. You will get the answer. Step number 1. S implies null is present? No. So step number 1 is bypass. Step number 2. Step number 2 is what? Step number 2 is your null production removal. There is no null production, bypass. Step number 3. Unit production. There is no unit production, bypass. Step number 4. Left recursion. See here carefully. Are you able to see any left recursion? See, there is indirect left recursion. Why indirect left recursion? Okay, so okay, so let me say in this way. If you are not able to find any left recursion, so you will bypass this step. Step number 5 will be apply necessary deductions. So you have to apply necessary deductions. So when you start applying necessary deduction, you will get the idea. See, we have got here capital A. We should get here a terminal, but we are not able to get here terminal. We are getting a non-terminal. So the only way is replace this non-terminal with RHS, with its RHS. So I am going to replace it, and then you will get the idea. So this capital A will be replaced by what? Like this now. Okay. So this A will be replaced by double S, and this A will be replaced by B. And after that, we will have capital A. So here we have got it. Now A goes to SS or B. Now see here carefully, you have got left recursion. So you have to remove it. Otherwise, it won't be converted into GNF. Okay. Why it won't be converted into GNF? Because we need here terminal. But S implies S means what? You will see here carefully. If you put the value of S, you will again say double SA and so on. So you won't be able to get here terminal. See here carefully. I am just giving you intuitive idea. I'm not going into detail. Okay, so I'm just saying, see here, S implies S now. So if you put the value of S, you will get again SSA and so on. So you won't be able to get here terminal. Okay, so you have to remove this left recursion. So now the question arises, how will you remove this left recursion? This is very simple task. Okay, this is very simple task. We have already told you many times. So just try to remove left recursion from here. Okay, so you will get S implies what? S implies, see here, I am going to write it A alpha 1, beta 1, beta 2. So I will write S implies beta 1, beta 2, beta 1Z, beta 2Z. Z implies alpha 1 or alpha 1 Z. We have removed left recursion. Okay. Now what we are going to see here. See, we have removed this. We have removed the left recursion. Okay. And the only production rule which was remaining is this. So we will write this also. A implies SS or B. Okay. Now tell me what should be the next thing. See here carefully. S is already in the GNF. See here carefully. S is already in the GNF. So that's it. We have got the idea. So just and see here. Z is not in GNF because here we have a non-terminal S, and this non-terminal is already in GNF. So you can replace this non-terminal S by its RHS. And here also this is creating problem. This is already in GNF. This is creating problem. So replace this S by this this RHS. You will get the answer. Okay. So now nothing is left. So let me write it properly. I will write S implies BA or BAZ or AZ. Now Z implies you have to put everything now and followed by capital A. So write everything followed by capital A. Everything followed by capital A. Next, again everything followed by capital AZ. Everything followed by capital AZ. Everything means what here? This thing. Okay. By capital AZ. BA capital AZ. A capital AZ. B capital AZ. Capital AZ. Then AZ capital AZ. Now Z is converted. See here carefully. Z is converted. Okay, now is the turn of capital A. So this S will be replaced by this, and S will be copy pasted. Okay, so S will be pasted or concatenated with each and every RHS. So do it carefully. A implies BAS, AS, BAZS, AZS, small b, because small b you have to keep it. Okay. Yeah, that's it. So this is your converted grammar, and I will say with confidence that this grammar, okay, this grammar and your given grammar both are exactly equivalent. The only thing is this is in CFG but not in GNF. This is in GNF also. Okay, so please note it down carefully. Okay, or let me let me put everything on one slide so that you can note it down. Yeah. Next is advantages of GNF. So we have two major advantages. Number of steps needed to generate string. Number of steps needed to generate string of length n is n. How will you prove it? See here carefully. Each and every step. See here also. Each and every step, we will get one terminal, or you can say exactly one terminal. See here. When we apply S implies BA, we will get one terminal. Here also one terminal, here also one, here also one, and so on. See here carefully. Each and every step will give us exactly one terminal. And if you want to generate string of length n, and each step is giving us one terminal, so what this means that we will need exactly n step to generate any string. If you are not able to follow, please rewind the video and watch it again. I'm not going to repeat it again and again. Okay. So okay. So okay, so let me repeat it one more time. Okay, if you are not able to follow, let me repeat it one more time. I'm saying number of steps needed to generate string of length n is n. How will you prove it? If string is of length n, that means what? It will have n terminal symbols now. It will have n terminal symbol, and each and every step of GNF is what? It is giving us one terminal. Each and every step is giving us one terminal. So that means what? How many steps we needed? Obviously n steps. That's it. Okay. So now I think you have got the crystal clear idea. Okay. Now step number 2 is PDA can be converted to GNF easily. So this I will explain it in PDA, and actually it is a basic course, so I'm not going to explain this in pretty much detail, but I'm just giving you idea that PDA can be converted to GNF very, very easily. Okay, so if you want to convert PDA to context-free grammar, then that context-free grammar will be in GNF. That's it. Okay. Yeah, so this is all about normal forms. In the next lecture, we are going to start the next topic, and I think the topic is PDA. That is very, very important topic. Okay. So thank you so much. Bye-bye.